Hello, everyone, and welcome to another virtual Eclipse community meetup. Joining us today, we have Simon Hoikis to discuss Eclipse iceoryx blueberry speeds up AUTOSAR Adaptive. If you have any questions for Simon as we move through today's presentation, feel free to ask in the chat or using the Ask a Questions tab. So without any further delay, Simon, over to you.
Hi, everyone. Thanks for the introduction. I'm Simon, and I work at Apex AI, mainly as a maintainer for Eclipse iceoryx, which we also at Apex use in our product Apex middleware, and I'm also caring about that at Apex. Cool. Today, I want to talk about Eclipse iceoryx Blueberry, our latest release, and how it can speed up your AUTOSAR adaptive implementation. Okay, so let's get started. A quick overview. In the first chapter, I want to discuss why does inter-process communication or IPC matter. Then I'm going to discuss briefly the history from AUTOSAR Classic to AUTOSAR Adaptive. I'm going to present the major two new features, request-response communication and the new refactored service discovery that were introduced with the Blueberry release. And also I'm going to present an example of how this latest Blueberry release can be integrated into automotive frameworks like Adaptive AUTOSAR. And I'm going to conclude the talk with a summary and a brief outlook. All right, so why does IPC matter? Actually, I mean, there's dozens of implementations out there. There's dbus, there's sockets, you name it. Why do we need another one? Well, all of these IPC mechanisms out there, they're very slow, and we need very fast IPC. So why do we need fast IPC? If you look at the automotive industry currently, autonomous driving is becoming more and more ubiquitous. Yeah, no matter where it's autonomous people movers, autonomous cars, autonomous agriculture vehicles, there are more and more products that come to the market. And what do they have in common, these devices and vehicles you can see here? Well, they have two things in common. The first one is their sensors produce a huge amount of data. Yeah, so this is typically gigabytes per second. And the second thing is this feedback loop. You might have seen this before in a bit different illustration, but basically they all sense the environment, produce an environment model with objects and point clouds. Then you plan your route accordingly and let the actuators act. And now typically on those modern systems, you're using an operating system like Linux or QNX. And if you think at these boxes here, the sense, plan, act, as applications, typically they're running in different applications on these modern operating systems. And these operating systems tend to have virtual address spaces, which means these applications can't see each other's memory. So for example, the Sense app here can't see the memory of the Planning app. And that's actually a good thing, because if you think about it, it's basically creates easier development because due to divide and conquer, you can split up your whole big software into different chunks. And the second improvement is also freedom from interference. So if, for example, the Sense application crashes, the Plan and the Act application, they can still run without being affected. But now we want to exchange data, as you can see on the arrows here. The Sense app wants to provide its data, the environment model, to the Planning app. So we need inter-process communication. And due to this large amount of data, this inter-process communication needs to be blazing fast for these kind of systems. All right. So in the next chapter, I want to discuss AUTOSAR and how the history of Eclipse iceoryx is connected to AUTOSAR. First of all, what is AUTOSAR? Well, AUTOSAR is both consortium and a standardization to exchange software modules between suppliers and OEMs in the automotive industry. And AUTOSAR Classic was first released 2004. With the first release, and AUTOSAR Classic typically runs on microcontroller-based devices, which means they have a common shared address space. And Providing or coming back to the initial feedback loop here, what you can see here is the Sense app exchanging data to a planet A and a planet B. And in AUTOSAR Classic, those applications, or AUTOSAR Classic calls them software components, they run in a so-called AUTOSAR runtime environment, or sometimes also referred to as RTE. And this RTE has a problem, because for every subscriber, it does a copy. Yeah. So when exchanging this data, so you can imagine this is not acceptable for systems like autonomous driving, where a huge amount of data needs to be processed, because the latency in the runtime, as you can see here on the right side, is increasing with the message size. So how can we solve this problem? How can we address this? Well, we can address this with a zero copy API. And now, what is a zero copy API? Again, this very same example, the feedback loop. And the Sense app here first allocates memory in a shared memory pool, then writes its data to the shared memory pool just once, a single time, and then sends the sample to the receiving applications or software components. And sending the sample here means just exchanging a pointer. So this is the reason why it's blazing fast. And the subscribing applications or software components just read from the very same memory location. So we only have a single copy. As you can imagine, as depicted on the right side here, the latency runtime then becomes dependent from the message size. And beginning in 2009, this was first implemented with the DADI middleware. And you might ask yourself, what exactly is DADI? So let's jump right next to the next slide. And here I want to discuss briefly the history of Eclipse iceoryx and how the history of iceoryx is connected to both DADI and also AUTOSAR. All right. So in 2009, or between 2009 and 2012, Bosch created its zero copy middleware called DADI, which stands for Driver Assistance Data Delivery. And this was especially made for advanced driver assistance systems, sometimes also referred to as ADAS. And you can imagine they produce nowadays this huge amount of data. And today, this DADI middleware is running on millions of microcontroller-based ECUs to avoid those copies and to save this precious runtime on these resource-constrained devices. So it's very, very likely that you have it running in your car today as well. Okay, in 2016 then, due to the need for a high-performance API, Bosch decided to contribute the zero copy API of DADI to the AUTOSAR Adaptive gremium or consortium or standard, together with BMW, and define the module called ARACOM. This is a module of Adaptive AUTOSAR. But you might ask yourself, what is exactly Adaptive AUTOSAR? Well, Adaptive AUTOSAR is the next generation standard of AUTOSAR. So it's not AUTOSAR Classic anymore, but it is targeting POSIX-based devices. So devices which run an operating system like Linux or QNX. And in the meantime, then Bosch started the development of a POSIX middleware based on DADI, targeting ARACOM, so this communication module of Adaptive AUTOSAR. And back then, I contributed the first shared memory implementation, combining DADI together with the POSIX shared memory APIs. And then in 2019, Bosch open sourced the POSIX middleware as Eclipse iceoryx. So in summary, you can say that DADI is quite literally the DADI of iceoryx. All right. So just to get everyone on the same page, some of you might know about iceoryx already, but just a quick summary, what is it exactly? It's a zero copy inter-process communication for safety critical applications. And it's fast, flexible, but also dependable. Fast, as its message transfer latency can be as low as 1 microsecond, depending on the hardware. And flexible because it runs on various operating systems, not only POSIX systems nowadays. It has a standalone API, but typically it's used inside frameworks. For example, many automotive frameworks integrated isoryx already. There's, for example, eCal from Continental. There's Apex middleware. We are using it at Apex AI. The RTE VRTE from ETAS, a Bosch subsidiary, is also using it. Eclipse Cyclone DDS used it to speed up their Cyclone DDS implementation. And AUTOSAR AP from Evans System, building AUTOSAR products, is also using it. But at the same time, it's dependable. So it's developed according to automotive requirements right from the beginning, as you've seen. And what does this mean? This means, for example, that we don't use the heap, but only static memory. So in this static memory, we then use custom STL implementations. So for example, if you look at our vector implementation, this vector implementation has a fixed size. And additionally, when accessing elements in this vector, we always perform out-of-bounds checks. So this is a very good example of how the software differs compared to, let's say, traditional software in desktop environments. We're talking about safety-critical software here. All right. Next up, let's talk about a bit about the new features in the latest Blueberry release. The first feature that I want to talk about is the request response communication feature. It's sometimes also in the literature or in other frameworks referred to as a remote procedure call, or short RPC. So basically, we're calling from one application a method in the other application. So here in this example, the client application calls the method compute_sum with the arguments 1 and 3, and sends this request over to the server application. The server application then does the actual method call and sends over the response, which is here, of course, 4, and the client gets this response. And using this new isoryx API, this can be implemented with polling, so basically with a while true loop, let's say, but it can also be implemented reactively and event-driven. And this event-driven reactive way of implementing this is probably what you want, because it saves you this precious CPU time and CPU cycle time. So this is what I'm going to talk about on the next slides. Okay, so let's have a look here. So on the left side, we have the client app. It has a wait set and a client. On the right side, we have the server app. It has a listener and a server. Wait set and listener are these event-driven building blocks that can be used to wake up like without a busy wait. And in the middle, we have shared memory. So what happens first? First of all, the client allocates some memory in shared memory. Then we write our request to this shared memory, and then we send the request. And sending means here, as you have seen also earlier, just sending a pointer. So no data is copied ever. Just send over the pointer to the server app and ring the bell so that the listener actually wakes up and executes the callback that we've defined before. And in this callback then, the server again allocates memory, of course, because we want to send the response. And based on the request and the internal method, whatever this might be, for example, compute_sum, we calculate the response and then write the response to shared memory. And then it's all the way back. We send over the pointer, the wait set wakes up, like with a non-busy wait, and the response is received. You can check out the complete example on the link below. All right, so how does this look in the code if you don't have time, for example, for checking it out? Well, we are using a functional approach here. What does this mean? This means I'm going to go here from the very beginning to the end and just show you how this looks in code for you to give you a feeling. So this reads like a story because we use this functional approach. So the client in the beginning, remember, loans memory in shared memory. And then if this is successful, we will call the callable, typically a lambda, which is inside the and then, which is inside the and then brackets. And This is called if the loan was successful. So if the loan was successful, we first set the sequence number. Then we write our member, for example, any kind of member that we need in this request. And then we send the request. And of course, this can fail. So we need to handle this. And if sending was unsuccessful, we need to, for example, bail out, or here, like it is done here, inform the user. And also loaning, of course, can fail. So of course, if we're getting out of memory problems, for example, if we've not defined our memory properly for the system, then this or else branch is being called, and the callable inside here is being called. All right, now we're going to the other side, the server side. Here, we first loan the request, and then if loaning was successful, we call the callable that you can see here on the top. And what do we do here? We do exactly what was presented before. We calculate the response based on the request. We write this again to shared memory, send it over to handle the SAT pass, of course, and also have to handle the SAT pass if we run into out of memory problems, which we, of course, never should be running into, like in a production system at least. Cool. And now going back to the other side, to the client again. The client takes in a while loop until there's no more messages available, samples available. And if this taking was successful, what we have to do is we have to have a look at the sequence ID, if this is the right one, if this fits the expected one. And if it fits the expected one, we can do something with the response, for example, print it out. And of course, if it wasn't the right one, we have to handle this case as well. Okay, so this was the request response communication pattern. Now to the next major new feature, the refactored service discovery. So here you can see on the left side, the publisher application with the publisher called radar left. And the publisher is being created from a so-called service description. This is how services are described in iceoryx. And I'll just take this example here to explain this a bit. So we have here the service radar. This is an abstract service. And this service is instantiated as the front left radar, and it transfers objects. So basically, the last string that you can see here is the one defining what is actually being transferred. And now imagine we have a subscriber app starting up, and the subscriber app isn't aware of what kind of samples or topics are currently offered in the system. And this is exactly what the service discovery is for. So with the service discovery, we can query the service registry, which is residing in the shared memory. So let's do that. We can query. And with querying, we can think about it like a super simple database query. And we can also use wildcards here. So for example, here, we're just querying for all the radar services. And then based on the search result, we can create our radar left subscriber and then actually receive this data from the publisher. But of course, for example, if you think now this is an ADAS system and we are in the boot phase and the camera is maybe booting up a bit slower, a few milliseconds behind, then once the camera is available, another publisher is being created here, camera front, again of the service camera, instance front, and what is being transferred is the image. And then we need to write this information, of course, to the service registry. So once a new publisher is created, we write this information into shared memory to the database. And all of this can be done in a polling mode, like I've shown just a few seconds ago, but we can also do it reactively, event-driven, by attaching the service discovery object to either a wait set or a listener, and use it like you've seen in the request response communication example before. If you want to learn more about it, you can check out the example. All right. How does this look in the code? So here's just an excerpt from the service discovery. You can see there's this find service call. The first three arguments are the strings. They are optional because, of course, you can use like to do this wildcard search. The fourth one is a callable, which is called for each search result. And the signature, as you can see here, is void const service description. So you get, with each search result, you get a service description, and from the service description, then you can, for example, create a subscriber. And the last one is the messaging pattern, because this also works both for publish-subscribe communication, but also for request-response communication. So you can see you search for servers and publishers. Cool. Next up, I want to talk about an example that we created in the last few weeks, the integration into automotive frameworks, for example, like AUTOSAR Adaptive ARACOM. How does this exactly look like? So AUTOSAR Adaptive or ARACOM uses a terminology here from CORBA. So senders or publishers are typically called skeletons, and receivers or subscribers are called proxies. And typically such a proxy or a minimal skeleton or a minimal proxy, this code is typically being generated. So this is not handwritten, but generated from a meta model. And in this skeleton or also this proxy, there can be different kind of entities. So AUTOSAR has different entities. First, an event. This is basically the normal publish-subscribe communication. You push data to a receiver. Then you have a field. A field always has a value, and the field can be manipulated from the receiver side. And you have methods, and these are exactly remote procedure calls. Yeah, what we've seen before in the example. So how does this example work? Well, first, of course, our proxy application needs to discover the service minimal skeleton. And in AUTOSAR, a service is always defined as a package of different entities. So here, event, field, and method. And we use the service discovery to discover it. And once we've discovered it, once the skeleton application has started, we can create our respective minimal proxy object, which has these respective entities. So the event subscriber, field subscriber, and the method client. And then we can start sending data. And in this example, it's being also implemented with a non-busy wait. So not with polling, but in an event-driven manner. So we send data and wake up and print this data out. As I said earlier, the field subscriber can call get and set to manipulate the value of the field. Yeah, so that's a bit different. And the method can call or invoke the remote method call. And this can be done like with many, many different methods. So it's always one server with many, many, many different method clients. Okay, and the cool thing about this, the whole API is zero copy. So yeah, basically, AUTOSAR Adaptive, Eclipse iceoryx is ready to speed up your AUTOSAR Adaptive binding. If you want to check out the full example, you can find it in the link below. All right, let me conclude the talk with a brief summary and also give you an outlook on what's next on the agenda. Cool. So summed up, iceoryx, you've seen that iceoryx has a long history, and its predecessor is used in millions of cars. Also, the development of iceoryx heavily influenced AUTOSAR Adaptive, and its zero copy API became an industry standard. And the Blueberry release is feature complete for AUTOSAR Adaptive ARACOM. So once again, yeah, use it to speed up your AUTOSAR Adaptive binding. Regarding an outlook, what's next? So as you might know, Eclipse iceoryx is also widely used in the ROS community. ROS stands for Robot Operating System. And it is available currently, or currently the second version, ROS 2 is being developed. And there, an RMW, so a ROS middleware binding, was created a couple of years ago. And this is being actively used. And of course, this will be updated to Blueberry to also make use of the request-response communication feature. Then we at Apex, we will certify our Apex middleware product in the coming year. And yeah, these certification efforts, they will probably very likely result in a lot of patches going upstream. So you can stay tuned for that. And also in June 2020, Apex AI will publish a white paper on exactly this whole topic that I talked about, basically on AUTOSAR Adaptive and its use cases and how Eclipse iceoryx can help you speeding this up. So stay tuned and check out the website. Cool. With that being said, I welcome you to clone iceoryx on GitHub if you've not done so far, and check out the full API specification on iceoryx.io. And with that, I'm ready for any kind of questions.
Perfect. Awesome. So let me just quickly look at the Ask a Questions tab. There are no questions there. And there are no questions yet in the chat. So with that said, I just wanted to thank you for that excellent presentation today, Simon. And just a reminder, while I wrap things up here on my end, if the audience has any final questions, remarks, statements, please feel free to do so in the chat or the Ask a Questions tab. So we are actually looking to book more virtual Eclipse community meetups throughout 2022. So if you're interested in presenting, feel free to fill out the form, which I will link momentarily in the chat. So I'm just going to quickly look again. And the Ask a Questions, nothing there. Just a nice hand claps from Andy and Rex. And Andy is saying, thank you, Simon, for the great presentation. Perfect. Great. All right, and I've just linked the form if anybody is interested in hosting a talk. And that's that. So it doesn't look like there's anything else. I just wanted to say thank you again, and I hope you all enjoy the rest of your day.
Bye-bye.
Bye. Thank you.